Hello friends, welcome to my lecture on evaluation of real integrals using residues. This is the fourth lecture on this topic. In this lecture, we shall consider certain real integrals for which some special techniques and some special contours are needed. So, let us consider the integral over minus infinity to infinity x cos pi x over x square plus 2x plus 5 into dx. Now, here you can see we have considered such type of integrals in the previous lecture, but there what we had was that we considered integral over minus infinity to infinity f x cos s x dx, and we assumed that f x is a rational function say p x by q x, where q x is not 0 for any real x, and degree of q x minus degree of p x is greater than or equal to 2. But here we notice that although f x is equal to x over x square plus 2x plus 5, that is, it is a rational function, okay, but here the degree of the denominator is 2 while the degree of the numerator is 1. So, the difference in the degrees of the denominator and the numerator is not greater than or equal to 2, and therefore, the technique which we applied to show that the integral along gamma, that is integral along the semicircle goes to 0 as r goes to infinity, that technique will have to be modified in order to show that the integral along gamma of the function f z into e to the power I pi z. Here we will have, we are taking cos pi x, so we will be considering e to the power I pi z. So, integral over gamma f z e to the power I pi z dz goes to 0. So, we will have to make a certain modification in that technique to show that the integral along gamma goes to 0. So, what we do is, let us consider the contour integral z e to the power I pi z over z square plus 2z plus 5 dz. Now, you can see that f z is equal to z e to the power I pi z over z square plus 2z plus 5. So, it will have poles wherever the denominator z square plus 2z plus 5 is equal to 0. Now, z square plus 2z plus 5 equal to 0 gives you z equal to minus 2 plus minus under root 4 minus 20 divided by 2, which will be equal to minus 2 plus minus 4 I divided by 2, or we can say minus 1 plus minus 2 I. Now, here again we shall be considering the contour which consists of the semicircle with center at origin of radius r and center at the origin, and the line segment from minus r to plus r. So, you can see that here there are two poles. One pole lies at minus 1 minus 2 I, minus 1 minus 2 I will be in the third quadrant here, minus 1 minus 2 I, and minus 1 plus 2 I will be here in the second quadrant. Okay. So, and moreover you notice that the denominator, suppose if denominator is phi z, then phi prime z is equal to 2z plus 2. Okay. So, at z equal to minus 1 plus 2 I, what we get, phi prime minus 1 plus 2 I equal to minus 2 plus 4 I plus 2. Okay. So, this is equal to 4 I. Therefore, phi prime minus 1 plus 2 I is not equal to 0, and so we can say that at minus 1 plus 2 I the function f z has a simple pole. Okay. Actually, it has simple poles at both of these points, minus 1 plus minus 2 I, but out of these two poles, the pole at minus 1 plus 2 I lies in the upper half plane, and our contour which we have taken, contour C, consists of this semicircle gamma, and the line segment from minus r to r contains the simple pole at z equal to minus 1 plus 2I when you take R to be sufficiently large. So, we shall be only considering the residue at the simple pole which lies in the upper half plane. So, let us find the residue of f z at z equal to minus 1 plus 2I. So, we have in order to find this, we consider residue of f z at z equal to minus 1 plus 2I will be equal to we have z e to power I pi z over z square plus 2z plus 5. So, we will differentiate the denominator and put the value of z. So, we have z e to the power I pi z divided by 2z plus 2 and you put the value of z equal to minus 1 plus 2I. So, what we will get minus 1 plus 2I into e to the power I pi minus 1 plus 2I divided by minus 2 plus 4I plus 2. So, this will cancel with this and what we will get here we have minus 1 plus 2I divided by 4I and then we have e to the power minus I pi into e to the power minus 2 pi. E to power I pi into 2I is e to power minus 2 pi. So, e to power minus I pi is cos pi minus I sin pi and therefore, it is minus 1. So, we get 2I minus 1 divided by 4I into e to the power minus 2 pi. We can simplify it further and write it as 1 over I is minus I. So, we will have 1 over I is minus I. So, when you multiply minus I to 2I minus 1, what you will get? Minus 2I square means 2 and minus I when you multiply to minus 1 you get plus I. Okay. So, and so minus 1 when you multiply here we get 1 minus 2I actually 1 minus 2I. Now, 1 over I is minus I. Okay. So, 1 over 4 and we multiply minus I here. So, we get minus I and then minus plus 2I square, plus 2I square means minus 2. Okay. So, we get minus 1 by 4 I plus 2 into e to the power minus 2 pi. Okay. So, we get this residue of f z at z equal to minus 1 plus 2 I comes out to be minus 1 by 4 2 plus I e to the power minus 2 pi. Now, taking r to be sufficiently large, okay, the integral over c can be written as integral over gamma plus integral over minus r to r f z dz. So, integral over minus r to r, now f z becomes f x because we are moving along the x axis. So, f z becomes f x and dz becomes dx. So, integral over minus r to r f x dx plus integral over gamma f z dz equal to integral over c f z dz. Now, by residue theorem, integral over c f z dz equal to 2 pi I times sum of residues at the poles in the upper half plane. So, we get 2 pi I, we multiply to that value and we get minus 2 pi I by 4 2 plus I into e to the power minus 2 pi and then we have here we have integral over minus infinity to infinity f x dx plus limit r tends to infinity integral over gamma f z dz. Okay. Now, we will show that limit of integral over gamma f z dz as r goes to infinity is 0. Okay. So, let us prove this. So, we have f z equal to z e to the power I z. So, we will let us consider integral over gamma f z dz, f z into f z we have taken as z e to power I pi z over z square plus 2z plus 5. Okay. So, we put that. So, dz is equal to modulus of integral over gamma z e to the power I pi z dz divided by z square plus 2z plus 5. Okay. So, this is less than or equal to integral over modulus of z mod of e to the power I pi z, okay, and mod of dz divided by modulus of z square minus 2 times mod of z minus 5, using the fact that mod of z1 minus z2 is greater than or equal to mod of Z1 minus mod of Z2. This follows from the triangle inequality. So, using this triangle inequality, this result from the triangle inequality, we get the modulus of Z square plus 2Z plus 5 is greater than or equal to mod of Z square minus 2 times mod of Z minus 5. Okay. Now, gamma is the semicircle with center at origin, radius r. So, mod of Z equal to r, okay, and 0 less than or equal to theta less than or equal to pi. We can write Z equal to, so we can write Z equal to r e to the power I theta, small r we should put. So, Z equal to r e I theta, 0 less than or equal to theta less than or equal to pi. Now, so mod of Z we shall replace by r, mod of dz, dz is equal to r e to the power I theta into I d theta. So, mod of dz will be equal to r d theta. Okay. And what is e to the power I pi z? Mod of e to the power I pi z is equal to mod of e to the power I pi, and then z is r cos theta plus I r sin theta. So, this is equal to mod of e to the power I pi r cos theta into modulus of e to the power minus pi r sin theta. Okay. Modulus of e to the power I pi r cos theta is equal to 1 and e to the power minus pi r sin theta is greater than or equal to 0. So, we have put greater than 0. So, we can write it as e to the power minus pi r sin theta. Okay. So, this can be written equal to integral 0 to pi r e to the power minus pi r sin theta into r d theta divided by r square minus 2 r minus 5. Okay. Now, this is equal to r square upon r square minus 2 r minus 5 integral 0 to pi e to the power minus pi r sin theta d theta. Now, let us notice the difference between this expression and the expression that we used to get when we had this in the coefficient of cos s x, we had the rational function where degree of the denominator was at least 2 units higher than the degree of the numerator. Here the denominator has only 1 degree higher than the degree of the numerator. Okay. So, when the degree of the denominator was at least 2 units higher than the degree of the denominator, what we did was this e to the power minus r pi sin theta be replaced by 1. This is always less than or equal to 1. So, we replaced it by 1, and here we had the difference in the degree of the numerator and denominator was 1. Okay. And so, when r tends to infinity, this expression tended to 0 there, but here what is happening is that because the difference in the degrees of the denominator and numerator is only 1, you can see that the degree of the numerator is 2 and the degree of the denominator is also 2, and therefore, we cannot replace this by 1. If we replace this by 1, then this will not go to 0 as r goes to infinity, due to the fact that the degrees in the numerator and denominator are equal. Okay. So, now what we do is we use the Jordan's inequality, okay, and Jordan's inequality says that okay, let me first use a property of the definite integral, that when you replace the integrand by the variable of integration is theta. When you replace theta by pi minus theta, there is no change in the value of the integral. So, it is 2 r square upon r square minus 2 r minus 5, 0 to pi by 2. We can use this property of the definite integral. Okay. So, this follows because sin pi minus theta is sin theta. So, there is no change when we replace theta by pi minus theta. And now, what you do is use Jordan's inequality. And Jordan's inequality says that sin theta is greater than or equal to 2 theta over pi when theta belongs to 0 pi by 2. Okay. So, here we can write this is less than or equal to 2 r square upon r square minus 2 r minus 5, and then integral 0 to pi by 2 e to the power minus pi r into 2 theta over 5. So, minus 2 pi r theta divided by pi d theta. Okay. So, we replace sin theta by 2 theta over pi. So, 1 pi will cancel and we get e to the power minus 2 r theta d theta. Okay. Okay. So, let us go further. We have thus integral over gamma e to the x z e to the power I pi z dz divided by z square plus 2z plus 5, modulus of this is less than or equal to 2 r square over r square minus 2 r minus 5. R square minus 2 r minus 5 integral 0 to pi by 2, and we have e to the power minus 2 r theta d theta. Right. So, this is equal to 2 r square upon r square minus 2 r minus 5, and now we can easily integrate this. This is e to the power minus 2 r theta divided by minus 2 r. And what do we get here? 2 r square upon r square minus 2 r minus 5, and we will get now when you put pi by 2 here, e to the power minus pi r, okay, divided by minus 2 r, and then you get here minus 1 upon minus 2 r. Okay, so, this is 2 r we can cancel and we get r upon r square minus 2 r minus 5, 1 minus e raised to the power minus pi r. Now, you can see when r goes to infinity, e to the power minus pi r goes to 0. So, the expression inside the brackets goes to 1 as r goes to infinity, and this is a rational function where the degree of the denominator is 1 unit more than the degree of the numerator. So, this also goes to 0. So, this goes to 0 and this goes to 1. So, this goes to 0 into 1, okay, 0 into 1. So, this is 0 as r goes to infinity. So, this is how we prove that integral along gamma goes to 0 as z goes to as r goes to infinity. Okay. So, when we have proved this, then what do we get? Now, let us go back. Now, integral over minus infinity to infinity f x dx is equal to this quantity. This is 0 now. Okay. So, we get and this is how much? Minus pi I by 2 plus I into e to the power minus 2 pi. So, this we have written here minus pi I by 2 plus I e to the power minus 2 pi. Now, e to the power I pi x we can write as cos pi x plus I sin pi x. Okay. So, when we write cos pi x as e to the power I pi x as cos pi x plus I sin pi x and equate real and imaginary parts, then what we will get? Left side we will have on equating real parts, integral over minus infinity to infinity x cos pi x dx divided by x square plus 2x plus 5, and what is the real part here? When you multiply minus pi I by 2 to I square is minus 1. So, you will get pi by 2 e to the power minus 2 pi, and if you compare the imaginary parts, then left side imaginary part will be integral over minus infinity to infinity x sin pi x over x square plus 2x plus 5 dx, and here what we will get? Minus pi by 2 into 2, that is minus pi e to the power minus 2 pi. So, this is how we evaluate the value of the integral over minus infinity to infinity x cos pi x over x square plus 2x plus 5 dx. We remember that when the degree of the denominator is not 2 units higher than the degree of the numerator, then e to the power minus r pi sin theta will not be replaced by 1. We will be using the Jordan's inequality. First, we will convert the integral from 0 to pi to 0 to pi by 2, and then we shall replace sin theta by 2 theta over pi, so that we can integrate this expression. As such, into e to the power minus pi r sin theta d theta we cannot integrate. Okay. So, we replace sin theta by 2 theta over pi, and then we are able to integrate this and then take the limit as r goes to infinity. Okay. So, this is how we evaluate this integral. Now, let us go to next integral, where we shall be seeing that the integrand has a branch point. So, let us consider this integral over 0 to infinity x to the power p minus 1 over 1 plus x dx, where we have to show that the value of the integral is pi over sin p pi 0 less than p less than 1. Okay. Now, p is a value lying between 0 and 1. So, x to the power p minus 1 upon 1 plus x is a multivalued function, okay, and therefore, we have a branch point at x equal to 0. So, it is a singularity of the function, and therefore, we have to remove it in order to use the Cauchy residue theorem. So, we consider this kind of an contour. Okay. It consists of the contour C consists of the circle with its radius capital R, okay, B D E F G, okay, and then A B and G H. A B and G H coincide with the x axis, but they are shown separate, because so that for visual purposes we have shown them separately, okay, and then this small circle around C, around the origin of radius is epsilon, which is very small. Okay. This is just to exclude the singularity at x equal to 0. Okay. So, A B and G H, they coincide with x axis, but we have shown them separately, okay, to for visual purpose. So, let us see, we consider the corresponding contour integral. You see, corresponding to the integral 0 to infinity x to the power p minus 1 over 1 plus x dx, we consider the corresponding contour integral over c z to the power p minus 1 over 1 plus z dz. Now, this z to the power p minus 1 over 1 plus z dz is a multivalued function. So, that is why it has a singularity at z equal to 0. Now, we choose the contour C as shown in the figure, as shown in this figure. Okay. So, here the positive real axis is the branch line, this positive real axis is the branch line, and A B and G H are actually coincident with the x axis, but we are showing them separately for a visual purpose. Now, let us consider f z equal to z to the power p minus 1 over 1 plus z. Then f z has a simple pole at z equal to minus 1. The branch point at z equal to 0 we have removed by taking this small circle. Okay. So, f z has only one singularity, which is a simple pole at z equal to minus 1, okay, just minus 1. Now, a residue of f z at z equal to minus 1 is then, okay. So, when you consider this contour, okay, you move along A B, then you move along this outer circle, you move along G H, then H J R A, okay, and then you come back to B. Okay. So, we have this contour simple closed curve C, which contains the simple pole at z equal to minus 1. So, we have to find the residue of f z at z equal to minus 1, and in order to find the residue of f z at z equal to minus 1, what we do? Residue of f z at z equal to minus 1. Okay. We write limit z tends to minus 1 minus z plus 1 into z to the power p minus 1 divided by z plus 1. So, this will cancel with this and we will get minus 1 to the power p minus 1. Okay. So, minus 1 to the power p minus 1 will be this is minus 1 is e to the power I pi. Okay. So, e to the power I pi into to the power p minus 1. So, this is e to the power p minus 1 into I pi. So, residue of f z at z equal to minus 1 is e to the power p minus 1 into pi I. Now, by residue theorem, integral over a b plus integral over b d e f g plus integral over g h plus integral over h j r a, okay, is equal to 2 pi I into e to the power p minus 1 into pi I, 2 pi I times the residue at z equal to minus 1. So, this follows by the residue theorem. Now, integral over a b, let us write the integral over a b. This radius is epsilon. So, this is a is at a distance epsilon from origin. Okay. So, epsilon to r, and AB is coincident with the x axis. Okay. So, so you can say along AB x varies from epsilon to r, and we write z as x here. Okay. So, epsilon to r x to the power p minus 1 over 1 plus x dx, and then we move along the outer circle B D E F G. Okay. So, we write integral over 0 to 2 pi, or along the outer circle radius is capital R. So, z will be replaced by r e I theta raised to the power p minus 1, dz is I r e to the power I theta divided by 1 plus r e to the power I theta, and then we move along g h. Okay. When we move along g h is also coincident with x axis, but at the point g x is equal to r, and at the point h x is equal to epsilon. So, x varies from r to epsilon, but while starting from g to h we have taken one complete round about the origin, and therefore, theta now changes by 2 pi, and so we will put z as x e to the power 2 pi I. Okay. Not z as x, but z is equal to x into e to the power 2 pi I, because we have taken one round about the circle B D we have gone once around the circle B D E F G. So, x e to the power 2 pi I, then raised to the power p minus 1 over 1 plus x e to the power 2 pi I, and we have dx, dz is dx. Okay. Now, we have to move along h j a, this h j a. Okay. So, along h j a z equal to epsilon e to the power I theta. So, we have z equal to, and theta varies from 2 pi to 0, because we are moving now clockwise. So, theta varies from 0 to 2 pi to 0, and z equal to epsilon e to the power I theta to the power p minus 1, and then I for dz we will have epsilon e to the power I theta into I d theta divided by 1 plus epsilon e to the power I theta, which is equal to the right side 2 pi I e to the power p minus 1 into I pi. Okay. Now, what we will do, now let us take the limit as epsilon tends to 0 and capital R goes to infinity. We note that the second and fourth integral, this integral and this integral, they tend to 0, which we will showing later. Okay. So, these second and fourth integrals tend to 0, and these integral first and third integral, they approach to 0 to infinity. Okay. This goes to epsilon goes to 0, r goes to infinity. So, integral 0 to infinity x to the power p minus 1 over 1 plus x dx, and this will become infinity to 0 and this quantity. Okay. So, we have 0 to infinity x to the power p minus 1 over 1 plus x dx, and then infinity to 0, and here we will have e to the power 2 pi I into p minus 1 x to the power p minus 1. Now, in the denominator e to the power 2 pi I is equal to 1. So, we will have 1 plus x. So, what we have is this e to the power 2 pi I into p minus 1 x to the power p minus 1 over 1 plus x dx. Okay. Now, what we will do here, we can make the limit from minus infinity to 0 to infinity by writing a negative sign. So, we can write this left hand side as r, we can say 1 minus e raised to the power 2 pi into p minus 1 I. Okay. So, 1 minus e raised to the power 2 pi I p minus 1, and then integral 0 to infinity x to the power p minus 1 dx divided by 1 plus x equal to 2 pi I e to the power p minus 1 into pi I. Now, we can divide by this coefficient of this integral. So, integral over 0 to infinity x to the power p minus 1 dx divided by 1 plus x, this is equal to 2 pi I e to the power p minus 1 into pi I divided by 1 minus e to the power 2 pi into p minus 1 I. Okay. Now, this is 2 pi I, this is e to the power p pi I into e to the power minus pi I. So, e to the power minus pi I is minus 1. So, we will get minus e to the power pi I p, okay, because e to the power minus pi I is minus 1, and here what we will get 1 minus e raised to the power 2 pi I p into e to the power minus 2 pi I. E to the power minus 2 pi I is equal to 1. So, we will have 1 minus e to the power 2 pi I p. And now e to the power pi I p we will divide in the denominator and numerator. So, we will get 2 pi I minus 2 pi I divided by e to the power minus pi I p minus e to the power pi I p. When we divide by p e to the power pi I p in the numerator and denominator. Now, this is equal to 2 pi I divided by because of this minus 1, it is e to the power pi I p minus e to the power minus pi I p. Okay. Now, this is equal to pi divided by e to the power pi I p minus e to the power minus pi I p divided by 2 I. Okay. And this is pi over sin p pi. Okay. So, this is how we come to this result. Okay. Now, let us show that the second and fourth integrals go to 0 as epsilon goes to 0 and r goes to infinity. So, first we show that the second integral approaches 0 when epsilon goes to 0 and r goes to infinity. The second integral is integral over b d e f g z to the power p minus 1 over 1 plus z dz. Now, here z is equal to capital R e I theta. So, we have R e I theta to the power p minus 1 I r e to the power I theta over 1 plus R e I theta d theta and mod. Okay. Now, what do we get? This is equal to mod of integral 0 to 2 pi, and here what we will get e to the power I theta into p minus 1 into e to the power I theta. So, this is e to the power I p theta. Okay. So, and we have r to the power p, r to the power p e to the power I p theta into I d theta divided by 1 plus r I theta d theta. Okay. This is less than or equal to integral 0 to 2 pi r to the power p modulus of e to the power I p theta is 1. Okay, because e to the power I p theta is cos p theta plus I sin p theta, and modulus of that is always 1. So, this is, and mod of this is 1, mod of I is 1. So, we get r to the power p d theta, and r to the power r e I theta plus 1 is greater than or equal to r e I theta plus 1. This is greater than or equal to mod of r e I theta minus 1. Okay. This is r minus 1. So, this is r minus 1 here. Okay. So, this is equal to 2 pi r to the power p divided by r minus 1. Now, this quantity goes to 0 as r goes to infinity, because 0 is less than p less than 1. Okay. In view of 0 less than p less than 1, this power of r is less than 1. Here the power of r is 1, here the power of r is less than 1. So, this goes to 0 as r goes to infinity. So, this is how we show that this goes to 0. Now, let us come to this integral. Here what do we notice? In the fourth integral, modulus of integral 2 pi to 0. Now, this quantity, okay, this is equal to modulus of integral 2 pi to 0. This is equal to integral 2 pi to 0, then epsilon to the power p minus 1 into epsilon to the power p e to the power I times p minus 1 theta into e to the power I theta. So, e to the power I p theta, same thing as we have earlier, and then we have I d theta. So, into I d theta divided by 1 plus epsilon e to the power I theta. Now, this is less than or equal to you can say now this is integral over 2 pi to 0 we can write as minus integral 0 to 2 pi, and minus 1 mod will be equal to 1. So, we can write 0 to 2 pi, okay, and then epsilon to the power p mod of I p theta, and mod of I is 1. So, this is d theta divided by, here we will have 1 plus epsilon e I theta. When we take the modulus of this, since epsilon is very small, let us say this is greater than or equal to 1 minus epsilon. Okay. Instead of writing epsilon minus 1, we will write 1 minus epsilon, because epsilon is tending to 0. So, 1 minus epsilon. So, epsilon to the power p divided by 1 minus epsilon into 2 pi. Now, epsilon is going to 0. So, denominator goes to 1 and numerator goes to 0 because p lies between 0 and 1. So, this goes to 0. Okay. So, second and fourth integral go to 0, first and third integral we have combined and we have shown that the as epsilon goes to 0 r goes to infinity, we get the value of the integral 0 to infinity x to the power p minus 1 over 1 plus x dx equal to pi over sin p pi. With that I would like to end my lecture. Thank you very much for your attention.